Okay, so today it's lecture 4, and today I'm going to speak about two-level systems, and which is generalizable to multi-level systems coupled to baths, and also I'm going to speak about Jaynes-Cummings models and some exact solutions and consequences. Okay, so here is the system and bath of interest. Okay, so what I have is we have a effective two-level system. Okay, so and this is basically coupled to a bunch of harmonic oscillators. Okay, and this two-level system, you can either use up 2 or E, down 1 or G, and so on. So we'll use different notations, but basically this is the notation. So notice that now this is our new system bath and system bath. Okay, so this is quite different from what we discussed until now. And the important thing to note here is that there was a question some time ago that what happens when HS and HSR actually commute with each other, right? So what happens if HS, which is this, and HSR, which is this, what happens that if you calculate their commutation relations and it is 0? Okay, so this is exactly that kind of scenario. So notice that even if they commute with each other, you get interesting physics. So this is what I'm going to discuss. So obviously you can see that if that is the situation, this bath really doesn't help the system to exchange energy, but it can do other things to the system. Okay, so that is the thing that I'm going to discuss. So this kind of system bath coupling is basically called dephasing baths. Dephasing bath. Okay, so notice that sigma z of the system is coupled to this piece here. Okay, this is the bath. Okay, so here A is denoted as a bath, and there is no bosonic mode in the system, and there's only spin mode in the system. Okay, so now we are interested in, again as usual, calculating the reduced density matrix of the two-level system. So obviously this is the notation. So it's just a 2x2 matrix. Okay, the reduced density matrix is a 2x2 matrix. Okay, so now let me just proceed with the solution. So it just turns out that this model, it's traditionally it's the traditional version of the spin boson model. Okay, this is the spin boson model, and it turns out that this specific model has exact solutions. Okay, it has exact solutions, both time dynamics and steady state. Okay, and valid for any coupling. Okay, so now I'm going to discuss the exact solutions for the reduced density matrix. Okay, and then we will proceed. So how does this have exact solutions, right? So I will go a little faster here because I want to cover the later parts of my lecture today to make it consistent with the tutorial and tomorrow's lecture. But I'm outlining how to do the exact solution. Okay, so here the way we do the exact solution is, so remember that we basically can write the full density matrix evolution like this. Okay, and all we need to do is trace over the reservoirs. Okay, to do that, the way this is done is by going to this Polaron transformation. What the Polaron transformation does, it just diagonalizes this Hamiltonian. Okay, so there's a operator S, okay, which is defined this way. Okay, and this is A and this is sigma Z. This is A dagger A and sigma Z. Okay, so this operator acting on H in this way basically just diagonalizes the problem. Okay, so of course it may seem very sudden that I introduce this S, but basically there are systematic ways to sort of somewhat systematic ways to guess what is the right transformation that diagonalizes the Hamiltonian and so on. So I don't have time to go to that, but basically you see you have a diagonal Hamiltonian and there is some constant piece. Okay, so now the important point is that this thing of interest, okay, full density matrix, okay, can be now basically written in some steps. Okay, so I will not go through the steps because it is fairly clear. I have outlined very important steps here. So you can use this fact and make use of this to simplify the algebra. But let me go to the result. Okay, the result is very interesting. So let me skip the steps, and if we have time later, I can come and show you the come back and show you the details. But the solution, okay, the solution is given by this. So this is important. Okay, so this is the solution, and you can also show that the solution rho up t is basically rho up 0. Okay, so the interesting thing is the diagonal elements of the density matrix do not evolve, and this is how the off diagonal elements evolve. Okay, so this is the exact solution of a spin system coupled to a bosonic bath, where the initial condition is some spin part times thermal density operator for the bath. Okay, so this is exact solution. Okay, so I would encourage everyone to repeat this calculation. It's very interesting, and it's very nice to do this. So the diagonal elements do not evolve, and the off diagonal elements go in this way. Okay. Okay, so now going back to the problem.
So Manas, just quick question: does it mean that the expected number of particles in the up and down state basically doesn't change with time?
Exactly.
Okay.
So it just so the population just remains itself, and basically this bath is such that it is not able to exchange energy. Okay, so basically what happens is that that is why these are called dephasing baths. But nonetheless, it is affecting the off diagonal elements of density matrix, and basically that means it kills coherences. Okay, so if you see the word coherences and dephasing qubits and things like that, so this is what is happening. Okay,
so this is opposite of the other model where the off diagonal elements goes to 0 and then the only the diagonal element remains, right? The model you discussed in the first one.
Right. There in the model I discussed, the diagonal elements will go to some steady state.
Steady state, and off diagonal goes to 0, right?
Off diagonal goes to 0. Here what happens is that here it turns out that the diagonal remains stuck, okay, wherever it is. And the off diagonal element also actually, eventually decays to 0. So that so I'll explain this. This thing. Okay. So notice that if I give you initial value, I will basically get the value at any time t. Okay. So important point is that these notations are all basically consistent with whatever we discussed till now. So the important thing is that this is the exact result. Okay. This is the exact result for any time. So you can have exact time dynamics for any system bath coupling. Okay. So now let us analyze this a bit. Okay. So let us analyze what is going on with this expression. So obviously this is some oscillating piece. Okay. So not an issue. This is an oscillating piece. And this is also in the exponent, but it is essentially sum of various, sum over k over various trigonometric and hyperbolic functions, right? So what would happen is the following. So let me just add a page here. So what is presumably going to happen is that you have rho 1 2. Okay, let me just stick to up down, rho up down t as a function of t, and let's say you start from some initial condition. You see, it's awesome, and let's say you plot the real part, right? Because it's in principle a complex number, so it will keep oscillating. And what happens actually is that it just decays finally. Okay. Now, of course, that is hard to see from here because it's a complicated function. And now we will analyze this a bit. Okay, we'll analyze this function in some limits to get some intuition about what is happening with this term here. Okay. So please just keep in mind that this is the case where let me just write it like this. Rho. Okay, sorry, I keep switching between up, down, and down, down, and over time it evolves to rho up, up, 0, rho up, down, t, rho down, up, t, and rho down, down, 0. Okay, so this off-diagonal elements don't evolve at all. Okay, so so now let us analyze this a bit. This what I would call is this gamma t. Okay, everything on the at the exponent I have replaced this by gamma t. Okay, I'm just calling it gamma t. Okay, so now you see this gamma t. Interesting. I mean, this gamma t, of course, can be written in a integral form. Okay, and now interestingly, what happens is that you have this gamma t. Okay, and now let us choose a special path. Okay, because we want to compute something which gives us a feeling of rate, right? So ideally, I want to show that this gamma t is some minus gamma times t, right? So that means then this is the sort of time scale of dephasing. So if I now assume j of omega is same c omega, okay, and interestingly, if you assume that there is a high temperature limit, okay, you can exactly compute this integral, okay, and you will get this value. Okay, this is a very simple exercise. Okay, assume a high temperature limit and assume j omega is c omega, then you can exactly compute this integral and you will get this. Okay, so you will get gamma t, I am writing it at the top, minus 4 pi c by beta t. So rho up down t is something like e to the minus I omega q t, e to the minus 4 pi c by beta t. Oh, sorry, this is t. T. Okay. Okay, so in some limits, of course, you can explicitly, see that that function is this thing, and we can call this as dephasing rate. Dephasing rate. Okay, of course, this is, you don't have to do these limits, but if you want to see that indeed this is like rate, then you have to do some limits like this. Okay, so now let's not worry about that. So just remember that we have exact solutions of the spin boson model valid at any time for any system path coupling, and now the question is the following. The question is, what would happen if we actually solve the same Hamiltonian with a Lindblad master equation? Okay, so what will happen if I solve the same Hamiltonian with a Lindblad master equation? So of course, question is, why do you want to do that? It's important to note that even if I minorly change this Hamiltonian, then my exact solutions break down. Okay, so even if I add to this, if I add a piece omega sigma x, okay, then I'm pretty much I'm not able to do. I probably cannot do exact solutions. So eventually I have to resort to Lindblad equation. Okay, so it's good to do the Lindblad equation for this, get an idea of some benchmark, and then proceed with Lindblad equation for some generalized versions of spin boson model. Okay, so now you can do Lindblad equation, actually quantum master equation, strictly speaking. Let's call it quantum master equation. So you take this HS, HR, and HSR. Okay, you take this and use the machinery that I provided in my first few lectures. Okay, literally. So you literally identify what is SI gamma I. Remember, my HSR was SI gamma I, and do that, and we'll write down the we'll write down the Lindblad master equation. The
So
quantum.
Manas, just quick question.
Yeah.
So this solution, then it says that basically for two level system, you cannot inject energy by this harmonic oscillator bars, right?
If you couple it in this way, yeah. If you
But
want
then,
to inject, yeah.
Yes. So if you want to inject energy, like the infinite level system that you showed that, because that's like another harmonic oscillator.
Right.
So there you can inject energy. So like this finite level system, if you want to inject energy, what kind of coupling you need then?
Very good. So let me write down that. That's a very important question. So there, what you do is you can have a coupling like this. AK dagger sigma minus plus Hermitian conjugate. Okay. So here you can inject. Okay. And these are called dissipation Lindblads. Okay. These are called these will do is depending on the details, they will start decaying the spin. Okay.
So this is almost like the harmonic oscillator.
Absolutely.
Two-level harmonic oscillator, basically, right?
Absolutely, because you are creating facility to flip the spin.
Yeah. So this is like some RK dagger or something for the way K takes us to values.
That's right. This is analogous. This is analogous to AK dagger A dagger RK.
Yeah.
Okay. Yeah. In fact, I want to emphasize that many of these systems and physical systems have all these mechanisms. Sometimes the dephasing comes from some other reason, the dissipation comes from some other thing, and then what you have to do is you actually have to introduce sometimes multiple reservoirs. So you have to introduce a reservoir which is responsible for decay processes. Okay. So this is very important. In fact, at the end of my lecture, I will try to write down a big equation with all these processes taken into account. Yeah. Okay. So now, but going back to just our original Hamiltonian today, if you write down the quantum master equation, you will actually get this. Okay. So this is actually interesting. Please work it out. Okay. It is very straightforward, but quite nice. And you will get this L of sigma z. Okay, so remember L is already defined in my earlier lectures. So yes.
So whenever HS or HSR commute, you get a dephasing bar. Is it true?
It seems so. So indeed, it seems that when HS and HSR commute, you can say that first of all, you can say that energy doesn't get exchanged, right? Because by definition, HS is 0, right? So that is one statement. And typically what it will do is it will affect the off-dial elements of density matrices in the eigenbasis. Yeah. So this even if you generalize this, I have written that you can generalize this methods for multi-level systems and so on. And indeed there also this thing happens. Yeah. Okay. So now, so this is L of sigma z. So remember this L was already defined, and before we had L of A, okay, and we also had L of A dagger. Now we have L of sigma z. Okay. So, but this thing here is actually defined here. This thing is actually defined here. Okay. So this is one interesting point that actually is related to some questions Sanjib asked yesterday. So usually you evaluate these things at some frequency, right? Usually you evaluate these things at some frequency, and we had this discussion, and indeed it is some finite piece. Here it actually turns out that you evaluate it at 0. Okay, so this is it is related to some details of the calculation, but here you actually evaluate it at 0. Okay. And this piece here is actually here. Okay. So remember that most of the time what we do is we evaluated this at omega cavity or something, this also at omega cavity. Okay. But here actually you evaluate it at 0 frequency. And very interestingly, actually, so now what do I want to do? I have some result that I get from Lindblad master equation. I'm asking whether it gives me something coming from the something related to the exact result, right? That is the plan. And indeed, it turns out very interestingly that if I choose j omega to be c omega, okay, and I evaluate this quantity, okay, in the following way. If I evaluate this quantity as limit omega going to 0, j omega 1 plus 2 n omega, I actually get exactly the same gamma that I got from spin boson from the exact solution at high temperature. Okay, so the thing is that as long as you have some way to evaluate this carefully, you will get some decent rate. Okay, you'll get some decent rate, and then you can compare this rate to the rate that is obtained from exact solutions in some high temperature limit of their in their high temperature limit. Okay, and then immediately you can write that even from the quantum master equation, this is the solution. Okay, so this is very hello, was there any question?
Yeah, so the question, like, I had a question about, so you use this ohmic spectral density over here,
Yes, yes.
but then I would ask ki in the exact calculation we haven't given any specific form of spectral density. So why is this ohmic kind of a spatial spectral density or something?
No. Notice that it is true that we did not give a special form here, but if I
No,
want to
so
if I want to simplify this integral, okay, then I actually used the ohmic spectral bar density,
sorry,
okay,
sorry.
and some high temperature limit, and then I got this.
Okay.
Okay, yeah. Okay, so let me just make a point here that many times where people stop is they just stop here. Okay, they say that okay, we don't really care what it is. From some experiment we will try to add this term, and we will just call that as gamma tilde of 0, and typically it is called gamma subscript 5. Okay, so in the end you don't need to worry about whether you can get some precise analytical form. Okay, so you can just stop here and say that okay, what is the consequence of this? The consequence of this is that rho up, so rho 1 2, let me use rho 1 2 is e to the I omega qt e to the minus gamma tilde 0 t. This is the consequence. And in some experiment, if you manage to get this gamma out, then you will just phenomenologically just substitute it here, and then you will proceed to calculate other things. But here it's a nice way of actually comparing very precisely when quantum master equation actually agrees with the exact solutions of the spin boson model. So this is actually, it's nice to see really if you start with the same j and omega, same j of omega, whether you will get actually the right factor 2 pi c by beta. Okay, so even the factors, everything turn out to be same. So okay, so okay, so now let me so of course I mean, obviously you might have seen that if I choose j of omega to be some other thing, right, like omega square, okay, then obviously this quantity will actually, if you take the limit, you will actually end up getting 0, right? But that's not our point. Of course, you have to make sure that you take the right j of omega to get meaningful results. Okay, because we know in the physical system there is dephasing, so you have to choose it in such a way that their limit exists. Okay, so this is just one comment. Okay, so but for the original solution of the spin boson model, j of omega could have been something else. Okay, because this is well defined integrals. Okay. Okay, so this actually is one thing about dephasing baths, that these kind of things are typically computed at 0 frequency, and this comes out very nicely from calculations. Okay, so now let me just make one important procedure here, a step here. So let me actually,
Manas,
yes.
So since for the spin boson model, there is exact solution. Is it has anybody studied the evolution of the bath and
Uh,
reduced density matrix of the bath?
Reduced density matrix of the bath.
And what is the evolution of the bath?
Yeah, I'm not sure if someone has.
I'm saying whether one can see there are different assumptions that we make in the quantum master equation approach, and whether can one see those assumptions working at least in this model way, because we have exact solution.
Right, but you see, okay, I need to make one thing clear. When I say exact solution, I mean exact solution for the reduced density matrix of the system, assuming this initial condition.
Okay.
Right. So yeah, we have to be a little careful. Yeah.
Okay, but for chi-t is not known exactly. Chi-t.
Chi-t is not known exactly. Yeah, chi-t, the problem is chi-t, is known exactly in the sense of in a very formal way, but it's not very not in a very useful way. Yeah.
I see.
Yeah. It is the trace operation on the reservoir which one can do, make a lot of progress. That's what I mean.
Okay.
Right. So let me make one important. Hello.
So this. Yes. So are you? So So whenever the spectral density are, so you give this example of omega square. So are you saying that this kind of spectral densities are not possible, or you are saying that for such spectral densities you won't get dephasing, and if so, what should be the physical reason? Why don't we get dephasing
Right.
for?
Right. So okay. So that's a important question. So there are two ways to answer this question. Okay. So now you are asking purely from the point of view of quantum master equation, right? Right. So now you see. Suppose in the experiment they actually can measure this. Okay. Suppose in the experiment they can measure this quantity, and they see that there is a damping. Okay. They can measure some coherences and they see the damping. Then you know that there is a dephasing. Which means that the dephasing is coming from some underlying ohmic path. Okay, that is one way of seeing it. Okay, so from the experiment, you sort of see if there is dephasing, and then say that if there is dephasing, probably there's an ohmic path which is resulting in this dephasing. Another way is you can start from some microscopic bath and try to see whether it's a ohmic or non-ohmic or a super ohmic bath. And if it turns out that it is actually a super ohmic bath, then presumably this super ohmic bath will not result in dephasing. Okay, so it's a bit of both. Okay.
So we can rely master equation even if the spectral density is not ohmic. So gamma 0 equal to 0 is a correct result. I mean, so experiments will actually see it. Hopefully,
it could even be correct. Yeah. See, for example, imagine you have an experiment where you have some complicated phonon substrate. Okay, and you have some quantum dots. Okay, but imagine that for some reason we know that it's a super ohmic bath. Okay, then strictly speaking, if that is the only bath that is there, then if it is known from some other reason that it is a super ohmic bath, then presumably that bath cannot cause dephasing. Okay.
And why is that? I mean, do we have a physical understanding of why? I mean, what's
Right.
the? I mean,
so this thing, that bar spectral function with j of omega that I define, right? This bar spectral function actually for dephasing baths, what happens is that the rates that decide turn out to be the value of the bar spectral function at zero frequency. Okay, for dephasing baths. Okay, so that is the reason why if the bar spectral function goes to zero at zero frequency, it is unable to create dephasing mechanisms. Okay.
Thanks.
Okay, so now let me just make an important statement and then go to James Cummings model. So this is a bit important. So let us go back to this Lindblad master equation. So, okay, so I'm just going to write a few things here. So I'm just going to expand this commutator also. So minus I omega q by 2 sigma z rho. So sigma z rho minus rho sigma z. Okay, so this is one piece. Okay, and I'm going to expand this dephasing. So dephasing was minus gamma tilde 0. Okay, so I'm going to expand it here. So this is nothing but minus gamma tilde 0. I think by my definition, it would be something like sigma z rho sigma z minus sigma z square, which is just identity, so minus 2 rho. Okay, it will be something like this. And I think there's a half here. Okay, so so I might have got some coefficients wrong, but basically this is an example. Okay, so now this detail is not important. What is important is, let us say that you have 3 spin halves. Let us say you have 3 two-level systems. Okay, so what is the dimensionality of rho if you have 3 two-level systems? That will be 2 cube cross 2 cube. Okay, so that will be 8 by 8. Okay. Okay, so this is important even for today's tutorial. So that is 8 by 8, which means that this equation that I wrote here, the left-hand side is an 8 by 8 matrix. Okay, so what is important here is we do a procedure called vectorization. Okay, so you take this 8 by 8 matrix and you just vectorize it to get 64 cross 1. Okay, so then you will call it this. Okay, so this is basically a big vector now. Okay, so you take this matrix and just make it a column. Okay, I'll tell you why it is useful. Okay, so so if it was just a 2-level system, then it would be 2 by 2 matrix. Okay, so for 2-level system, let me just write for 2-level system. You have row 1 1, row 1 2, row 2 1, row 2 2. If I vectorize this, I will get row 1 1, row 1 2, row 2 1, row 2 2. Okay, just notation. Okay, no information is lost. Okay, so then this whole equation here, okay, this whole equation can actually be written as this. This is sometimes called Liouvillean. Okay, and this is equal to this times this. Okay, so we can rewrite the Lindblad master equation in this form. Okay, so this will be in my example 64 cross 1. This will be 64 cross this will be again 64 cross no, sorry, so this will be 64 cross 64, and this will be 64 cross 1. Okay, okay, so now you see, and this is the story for this whole thing was the story for 3 two-level systems. Okay, okay, please ask me questions if it is unclear, but I hope, I mean, I'm saying something simple, but it is needed for today's sorry, yeah, so this is okay, so for some, okay, this is 3 two-level systems. Now you see, now if I have this situation, okay, then I can trivially write the solution like this. Okay, okay, so now that is the thing. So then this matrix, which is now 64 cross 64, okay, is going to be a non-Hermitian matrix, right? It has everything now. Okay, it has everything. It is going to be a non-Hermitian matrix. It has all these ingredients. Okay, and finally this matrix, which is a non-Hermitian matrix, results in a lot of things. So the eigenvalues of this non-Hermitian matrix will be complex eigenvalues. Okay, and we know that one of the if there is a steady state, then one of the eigenvalue has to be 0, right? And the eigenvector corresponding to the 0 eigenvalue is the steady state. Okay, I'm saying something very simple, but if there is a steady state, I can write 0 is equal to this times this. right? So the eigenvector corresponding to the zero eigenvalue is a steady state. Okay, and more interestingly, the spectrum of this, it lies in the complex plane. Okay, so imaginary part of real part of lambda and imaginary part of lambda. Okay, the eigenvalues lie in the complex plane, and we know that the eigenvalues, depending on your notation, cannot lie everywhere. For example, you cannot have eigenvalues with positive real part because the solution will blow up. So all the eigenvalues will have to sit here. Okay, all the eigenvalues will have to sit here, and if there is a steady state, one eigenvalue has to sit at the origin. Okay, so this quantity is very interesting. Okay, it has all, and the eigenvalue nearest to the next nearest eigenvalue to the zero eigenvalue, it dictates the approach to steady state. Okay, so a lot of information is hidden in these eigenvalues, and one can calculate, connect these distribution of these, connect these eigenvalues to non-Hermitian random matrices, and so on and so forth. So I'll talk about that in the next lecture, but basically Gregory introduced level spacing and things like that for Hermitian random matrices, and you can have similar notions for non-Hermitian random matrices, and that's a very active and interesting area of research presently. Okay, so that's what I wanted to.
Manas, a quick question.
Yeah.
This L. So is there a quickly get this L in general, or one has to look for a problem? Like given this original equation in terms of rho, can I just construct L immediately, or
absolutely.
one has to, yeah.
If you have given some Lindblad master equation, you can construct this L. There's a little bit of algorithm involved, which we will discuss.
Okay. Yeah. No, I'm saying like by applying something on the left and right, can one do that, or one has to actually write down these elements and find out what is the correct L?
There are some operations that may involve this vectorization procedure. Okay, so you have to do a little bit more algebra, but eventually you can write it in an elegant form and implement it. Yeah.
Okay.
Yeah. Okay. So
hi, Manas.
Yes. Hi.
Yeah. So I have a question that so you plotted the eigenvalues of the Liouville operator L.
Yes.
So is it always true that the zero eigenvalue, value is going to be non-degenerate?
No, it's not necessary. That's the thing. Okay. So in fact, that is the thing, right? Depending on the problem, if let's say it has 2 zero eigenvalues, okay, then that means that it is probably, then it's not a unique steady state. Okay. So all sorts of things can happen actually. So really you can have all sorts of possibilities, and sometimes you can have eigenvalues colliding when you change some parameters and things like that. Yeah. I'm just saying, if there is a unique steady state, then you can say that there is a zero eigenvalue.
Thanks.
Yeah, and the eigenvector that corresponds to that zero eigenvalue. Okay, so L rho equal to 0. So you can think of this as L. Let's be very careful with the notation. Let's call this kind of L rho equal to 0 rho. So the eigenvector corresponding to this zero eigenvalue, E is the steady state. Okay. So now let me just go to a combination of all the above models. So this is very important. So this is called the Jaynes-Cummings model. So I've written a lot of sentences here, and if you read things, it will be quite clear. But let me just tell you the model. Okay, so this is a closed quantum system. No decay and dissipation mechanisms and so on. Just a closed quantum system. So Jaynes-Cummings model is, in some sense, is a combination of the two. Okay, you have a qubit, a two-level system, and you have a single photonic mode, and then you have this kind of qubit interacting with the two-level system. Qubit interacting with the photonic mode. Okay, so this is just single photonic mode coupled interacting with a single qubit. Okay, so this is still a closed system. Okay, no Lindblads. Okay, no Lindblads, just closed system, unitary evolution. Okay, So this model, of course, is very important. It has been realized in various settings and it has been used for various purposes, both from fundamental point of view and from technological applications and so on and so forth. So this has a long history. Okay, and in fact, I will add some references also here. So this is in some sense a good combination of our previous lectures, right? Because we had this before and we had this before. Now we just join them. Okay. Okay. So now you see so the Hilbert space is a combination of two. Okay. The two-level Hilbert space is GE. Okay, ground and excited, and the single mode Hilbert space is spanned by N. Okay, where N is just whole numbers. So the density matrix. So if you just had one two-level system, the density matrix of the reduced system would have been just 2 by 2. Here it is actually 2 infinity by 2 infinity, right? Because you have 2 for the qubit and infinite for the single mode. Okay, and so this is the dimension. Okay, so quickly it becomes complicated if you add a bosonic mode, right? So that's the point I'm trying to make. Okay. So of course, in reality, for numerical implementation, what you do is you cut off, right? You basically say, let us just cut off this N as 0, 1, 2 up to some N's cut. Okay. And then the dimensionality will be 2N cut, 2N cut. Okay. And then you hope that if I just increase the cutoff for the bosonic sector, my results don't change much. And so basically you are still able to work with some truncated Hilbert space. But strictly speaking, the Hilbert space is infinite dimensional, even the closed setup. Okay, so now what's going on? So obviously, if you see this, you may think that it is very difficult problem because of all these complications. But it turns out that this model has a U1 symmetry. And basically, let me just highlight the important points here. The rest is written here. There is this quantity here, okay, which commutes with the Jaynes-Cummings Hamiltonian. Okay, so this quantity here. Okay, so is this clear? So you see, independent. If you take this Hamiltonian, A dagger A doesn't commute with the Hamiltonian. Okay, sigma Z independently doesn't commute, but there is this combination that commutes with the Hamiltonian. Okay. So now this is the combination. So this combination, so let us just understand this combination. It counts the total number of excitations. Okay, it counts the total number of excitations in the qubits and the photons. Okay, so basically, if you have something like up and 7, then the total number of excitations is 8. If you have down and 7, then the total number of excitations is 7. Okay, this kind of thing. Okay, so and if I have up and 8, sorry, if I have down and 8, then the total number of excitations again 8. Okay, so it's very easy to check. I mean, you can basically take this N and just operate on some states. Okay. Part of it is coming from qubit and part of it is coming from bosonic sector, and you see that this Hamiltonian does not couple spaces with different excitation numbers. Okay, so it becomes block diagonal. Okay, this is very simple to see. Okay, it becomes block diagonal, although it looks very complicated Hamiltonian. It turns out to be integrable. It's exactly solvable model, and that's because it does not couple different spaces. Okay, so I hope that the statement is clear that if you have some space of total excitation P and some state with total excitation Q, then psi P H psi Q is basically 0. Okay, so these are all written in words, and I think it'll be quite clear if you read the sentences, but the idea is that you can block diagonalize the Hamiltonian, okay, which makes things enormously simple. Okay, so so this is how it's written. Okay, so I've written it in this piece. So you see, the Hilbert space span is a direct sum of these various spans. Okay, so basically, if you are here, if you are in this sector, you will just remain in this sector. Okay, because you see, this sector, you should understand this sector as what? G, for G, you say G is like 0 plus N equal to N. And this one is E is like 1 plus N minus 1 is equal to N. Okay, so this subspace has total excitation number N. This subspace, the small subspace here, has total excitation number N. Okay, and the Hamiltonian will act on the subspace and it will remain in the subspace. Okay, okay, so the Hamiltonian will just act on the subspace and it'll either, it can make you go from so what can the Hamiltonian make you do, right? It can make you go from Gn to En minus 1. It can make you go again from En minus 1 to Gn, but it cannot do Gn to Gn plus 1. It cannot do this. This is forbidden. Okay. Okay, so this is quite simple, and then your entire Hamiltonian will just be 2 by 2 form. Okay, so this subscript N is just denoting the excitation sector. Okay, so this is basically the excitation sector. In this excitation sector, it's just a 2 by 2 matrix. Okay. Are there any questions here? Is this clear? So you can act on, you can check it yourself, and it is quite nice that you say that, okay, you say that let me specify a sector where N is equal to 12. Okay, that means total excitation is 12. Then this will actually split into a small subspace G12 and E11. That's all. And then you can calculate H12 is equal to some 2 by 2 matrix. Because it cannot move away from this. It will remain G12 or E11 or some combination of the two, but it cannot be G17. It cannot become G17. Okay. So that is why this model actually becomes exactly solvable. Okay. And you can write exact solutions. Okay, so you can just write the eigenvalues and eigenvectors of this problem. Okay, this is the exact solution for the Jaynes-Cummings model, closed Jaynes-Cummings model. Okay, so please ask me questions if there is confusion about what we are calculating here. Because otherwise the later part of the lectures will become more complicated. So I hope that what is clear is what we have calculated in equation 30 and equation 31. So let me analyze these equations. Okay, then you'll understand it better. So let us say that we study a situation where omega c is very, very different. Let's say far greater than omega q. Okay, so the cavity frequency and qubit frequency are completely off resonant. Okay, in your original Hamiltonian. Okay, in your original Hamiltonian, imagine a situation that cavity frequency and qubit frequency are extremely off resonant. Okay, so you see what will happen. If you do that, you can see that this theta. So what is this theta? Then this theta n will be this will be will just be 0, right? Because this so theta n will be 0. Okay, so if theta n is 0, what will happen? You will have n plus, and then what will happen to these equations? You will have n plus is basically close to Gn, and n minus is close to En minus 1. Something like this. Okay, which means that the eigenstates are close to their decoupled states. Okay, so this is very easy to check, right? So then that means that the eigenstates are basically resembling their original states as if they were decoupled. So there is no mixing. There is no mixing. Okay. Now let's take the other extreme case where omega c is equal to omega q. Okay, this is called resonant case. This is resonant case. Okay, this is resonant case. Now what happens? Then it's immediately easy to see that this thing, if it is resonant case, theta n becomes pi by 4. Very trivial. Okay, theta n becomes pi by 4. Okay, because this will be infinity, and then you will get pi by 4. And then you see what happens. Then it seems that this will be, interestingly, what will happen is that this will be 1 over root 2 and this will be 1 over root 2. So that means the bare states are basically maximally superposed. Okay, so if it is resonance, then Gn and En minus 1 get basically maximally superposed. Okay, so is the eigenvalues and the eigenvectors clear? Is there any question here? And
Manas, can I ask a question?
Yes.
Yeah. So can I understand this in this way? Because since you have this two-level system, basically in the spin space,
right?
So therefore in the harmonic oscillator space, it can change the energy by just one unit if you just start with
right
one of the level, right?
Right.
So that's why it always remains in n minus 1 this thing basically.
That's right. Yeah. So
if I start with another system instead of a two-level, suppose I have a three-level system,
right,
and the harmonic oscillator.
Right.
So in that case, in the harmonic oscillator space, basically it will be restricted to 3 of the levels, I guess, right?
That's right. In fact, if you extend the Jaynes-Cummings model to some finite level system, then also you can exactly solve it, but this
it will become basically like
bigger.
The number of levels.
Exactly. So the block will become a little bigger. That's all.
Yeah.
Absolutely.
So if for a 3-level system, it will be like 3 by 3 basically.
That's right.
Okay.
Yeah. Okay. So now you see. Okay. So basically, the point is that the way you should think of this problem is that I have to give you n, right? I have to tell you what n is. I should say n is 8. Because you know that then it will always remain 8. Okay, so that is the thing. So obviously now you see what happens is that you can do again exact time dynamics. Okay, so let me so just for convenience I will work in the resonant case. Okay, resonant case is when omega c is equal to omega q. Okay, so the cavity and qubit have same frequencies. They are both very, very close to each other. Okay, and now let us study an initial value problem. Okay, this is the initial value problem. Okay, so I prepare an initial state in E and n minus 1. Okay, so let me be very clear here. So I'll prepare my initial state is E and n minus 1. So let me take n equal to 8. So I will prepare it in E and 7. Okay, and I will ask how will it will evolve. Obviously it will evolve, right? But what will it evolve as? It can become E7 to G8. Then again it will become E7. Then again it can become G8 and so on, right? So it will just evolve like this. And that solution is given here. Okay, that solution is given here. Okay, how it evolves. So that solution is given here. Okay, so we see that after some time period, some 2 pi by G root n. Okay, so the root n, the value of the time period depends on this n. Okay, so that is one important point. So it depends on which excitation sector you are in. That will sort of decide how fastly you oscillate. Okay, and the system. So with this time period, the system returns to its initial state. So the cavity plus qubit system periodically exchange energy like this. Okay, and this is called n photon Rabi oscillations. These are called n photon Rabi oscillations. Okay, now notice that even when n is equal to 1, okay. So when n is equal to 1, what happens? When n is equal to 1, this thing here, okay, becomes E0. So 0 photons, and the qubit is in excited state. And even then, you have these oscillations between E0 and G1. And these are called vacuum because you started with 0 in the boson sector. So these are called vacuum Rabi oscillations. Okay, so these are exact results, and you can just see how they oscillate and so on. Okay, so and the way they oscillate also depends on which excitation sector you are in, and the way they excite, they also oscillate even in vacuum. Okay. Okay, so I hope so. This is I think some time dynamics of James Cummings model is more or less there's some reasonable this thing. But now you can
so your equation 32 should not have psi 0 also, or what is psi 0?
Psi 0 is sort of inbuilt, because if you put t equal to 0 here, okay,
yes.
If you put t equal to 0, you will okay, let's do that actually. So let me add a page here. So if you put t equal to 0 here, so I'll get psi 0 equal to, then t is 0, so this is gone. Okay, then I have this is gone at t equal to 0 because it's sine function. Only this is remaining, so that will just be e n minus 1.
So you have started a particular initial condition.
Oh, absolutely. No, this is very important. This is, in fact, I will do some very interesting initial conditions next. So this initial condition is precisely e n minus 1.
Okay. Yeah.
So it's a very sort of it's a difficult initial condition in some sense, because you want some very perfect excited state and n minus 1 photons. But let us ask the question: what happens if you start with coherent state? Okay. So in some sense, it is like a classical state, right? A coherent state. And let us ask what will happen if psi 0 is nothing but, let us say, e, not n minus 1, some coherent state. Let me call it alpha. Okay. Let me just, this is my initial state. I'm free to choose my initial state, and then I run the same machinery. And then you see what happens. Okay, so here is the answer. So now if you choose a coherent state, which is given here, this is the evolution. Okay, so the evolution is a little bit more complicated, because the coherent state is essentially made of Fock states, bunch of Fock states. Each Fock state is evolving with some trigonometric function. So basically you have a bunch of trigonometric functions, right? So this perfect only single trigonometric function is what gave you nice oscillations. But coherent state has bunch of these Fock states, and so you have some complicated evolution, which is actually given by this expression. Okay, so now this is very interesting, because you see now because of this coherent state, this is what happens when you start with this. Okay, literally this thing. Okay, now I can ask what is probability that the qubit remains in an excited state. Okay, so this probability is nothing but, I can say it is nothing but psi t e psi t. Okay, and I know psi t, which is given here. Okay, and similarly I can find the probability where the qubit remains in the ground state. And this is the fascinating phenomena of collapse and revival. So this is what happens. So this is PG, probability that it's in a ground state. So what happens is that you sometimes have this collapse, and for a long time you think that it is over and done, and then you suddenly have these revivals. Okay, so these are very interesting phenomena in which this whole thing behaves in such a way that the qubit goes to the ground state. You see here, the qubit is in some state, let's say it's basically in some collapse state. Okay, and you think that it's all over, but then suddenly there's a revival, and then there is again some collapse and again some revival, and the periodicity is lost. Okay, the periodicity is lost, and basically this is the phenomena of collapse and revival. Okay, so similarly you can study some other maybe some combinations of Fock states. You could study, ask many sorts of questions here, and ask what is happening to the qubit. If I put the qubit inside a cavity, which for some reason is actually prepared already in a coherent state, and then I just implant one qubit, then you can ask what happens to the qubit. Does it get excited, or does it go to ground state? Does it stay long in some ground state, and so on and so forth. So this is the physics of collapse and revival. Okay. Okay, so this is something. So this is of course a very interesting feature of James Cummings model, and
Manas, there was a question in the chat box.
Yes. Sorry. Yeah. Even in the coherent state, so the question is, even in the coherent state, our initial qubit state is the excited one. Can we start from the ground state instead? Oh yeah, sure, absolutely. You can start with the ground state and you will still have some evolution, right? Because you can just say that you can just say that the psi 0 is g and some alpha. Okay, then it'll still have evolution. Okay, if you do some extremely, if you just start with some g and 0 Fock state, then there is no evolution. But if you start from g and alpha, then there is some evolution. Okay, right? So that is the important thing. So indeed, yeah, you can do this. Okay, where alpha is this parameter of this coherent state. Okay, so what I mean is the following. So here alpha can be any parameter, but let's say that in the previous example I started with e and n-1, right? But if I start with the initial state g and 0, okay, then it will not evolve, right? Then it will not evolve because how will it what will it go to, right? Because the total excitation number itself is 0, right? So that is the thing. Okay, but yeah, your qubit can be in the ground state. In fact, you can start with you can also start with situation where your qubit is in down, but the n is 2. Okay, so if qubit is let me use the word g and 2, this will go to e and 1. Again, this will go to g and 2. Again, this will go to e and 1, and so on. And it will go, it will keep oscillating like this with a frequency 2 pi g by root n, 2 pi by g root n. Okay, is that clear? Okay, so now let me tell you some nice, fascinating aspect of this James Cummings model. Just an example, okay? So just an example of a nice, fascinating aspect. So again, till now we are talking only about the closed quantum system, closed James Cummings model, okay? So now let me think of this kind of system. So this is James Cummings model. Okay, after all, let me just show this. So this is this, and this is this Hamiltonian. This is this Hamiltonian. So please see where I'm writing this. So this is this Hamiltonian. Okay. Similarly, this piece is this Hamiltonian. Okay. So this is two James Cummings models. Okay, and this coupling between the James Cummings models is like this. Okay. Okay. So this is a small generalization of James Cummings model called James Cummings dimer. Okay. So it is taking one James Cummings model, taking another James Cummings model, and making the facility for them to talk to each other only through J, where J is nothing but A1 dagger A2. So they can exchange photons. Okay. But the spins are not talking to each other directly. Of course, the spins are talking through, you can think that the spins are talking through J indirectly. So the spin talks to its own boson, its own cavity through G. Then the cavity talks through J, and then again the spin talks. Then the cavity talks to the other spin by G. So in this J-G square order, the spin is indirectly talking to each other. But okay, that's a different story. But this is the Hamiltonian. So I hope the Hamiltonian is clear. Right? I hope the Hamiltonian is clear. Is there any question about this Hamiltonian? Okay, so this Hamiltonian, of course, has been studied several times. Okay, this is James Cummings dimers, and there are attempts to scale up the system. So notice that in experiments, in this circuit QED experiments, there are several advantages. So one is that these experiments are tunable. Okay, so many things can be tuned. They are scalable. Okay, so they can be scaled up to several of these units to study some many body phenomena and large scale systems. And they're also versatile. Okay, you can have various geometries, you can have various lattice structures. So there's a lot of things that are possible in circuit QED systems.
Manas,
yeah.
This Hamiltonian in this last terms in the Z, should it be A1 and A2?
Sorry, which one? Where?
No, if you look at this Hamiltonian, look at the third terms on the first and second rows.
Yeah.
Is it sigma 1 plus A1, right?
This is sigma 1 A1. Okay.
Yeah, and sigma. Yeah. Okay.
Yeah, absolutely. Sorry about that. Yeah. Okay. So now what do they do? Okay. So this particular setup has, for example, been studied here in this theory paper, and there was an experiment at Princeton, looking at some aspect of this system. So what is the thing that they're interested in, right? So for example, you can ask. So this is just a sample example of some interesting thing that is possible. So you can ask, suppose I set up this system in an initial state such that in the first cavity there are some 20 bosons. Okay, one. Okay, in the first cavity, and in the second cavity it is say empty. This is say empty. Okay. So and let's say I'm interested in this kind of imbalance. Okay, I'm interested in this imbalance term. Okay, which is basically, this imbalance term is basically n1 minus n2 by n1 plus n2. Okay. So what does this mean? So what is z of 0? Z of 0 is nothing but 20 minus 0 by 20 plus 0, right? So z of 0 is 1. Okay. So now the question is, let us say that I let the system evolve. Okay. Now it's a complicated evolution, right? These 20 bosons are going to talk to this qubit, and they are going to leak out to the next cavity, and so on and so forth, right? So it's very complicated dynamics, right? So then the question is, after some time, what happens to this Z? Okay. Now, I think from here you can see that if Z of 0 is 1, this is how it is prepared, right? I am putting bosons in the first unit, and I am just letting it evolve. Now, if Z at t, okay, let's say at some time, is still close to 1, what does that mean? Let's say Z of t remains at 1. It basically means that the bosons here, they have got trapped, right? They are somehow unable to leak out to the next cavity, right? So and imagine Z of t actually goes from 1 to minus 1. What does this mean? This means that these bosons, these 20 bosons are going from this cavity to that cavity, then they're sloshing back and forth. Because notice, this is a closed quantum system, okay? So of course, in experiments and even in the theory, they consider dissipation, but just to simplify it, I'm just saying that you have these 20 bosons, slashing back and forth, because you cannot escape, right? It's if you think of it as an isolated system. And what happens, interestingly, is you have this very nice, interesting situation here, okay? That when G is less than some G critical, okay? When G, what is G? G is the light matter interaction. G is the light matter interaction within each cavity. So the G is here. Okay. So when this G is less than some G critical, it turns out that these bosons, they keep sloshing back and forth. Okay. But when G is greater than G critical, the bosons get trapped. They get localized wherever they are. Okay. So what happens is that because of this G, okay, if there was no qubit, okay, if there was no qubit at all, imagine you just have cavities, then something like this would happen, okay, because no qubit would be putting G to 0, right? If G is 0, that means I sort of forget the existence of a qubit completely, okay? So you see, so you have all this interesting physics where you can study self-trapping, and this is coming mainly because of interactions, purely because of interactions. Not only just interactions, but also some strong enough interactions, okay? And the interactions are somehow resulting in localization, Okay, so this has been realized in experiments, and now there are some generalizations of this and so on and so forth. And you can imagine that if you create like several such units, then and you say populate every alternate unit, then you can calculate the imbalance in the whole system, and several such units are in fact already prepared. There are experiments with like many of these units and so on and so forth. May not be measuring this, but measuring something else, but there are experiments which are able to prepare this kind of lattice systems with all this interesting physics. Okay, so is that so I hope the physics is clear here. And the G critical, of course, is a little bit complicated story, but they are but it turns out that this G critical I think goes as square root of n or something. But okay, so I'll try to
Manas,
yeah.
okay, this so this two qubit system, can you still solve it exactly, or?
No, I think not actually. You cannot do it exactly. This is actually so this is, I think you cannot write exact solutions for this. No.
Okay, so this transition, it's a numerical observation.
This transition is a numerical observation, and also you can do some semi-classics and get some this thing about this transition. Yeah.
Okay.
Right.
Yeah. Thanks.
So one thing I want to say, there is a limit. So maybe there's a limit when omega q minus omega c, okay, which is the difference between the qubit and cavity frequency. When G over omega q minus omega c is small, okay, when this is small, you can actually do some perturbation theory and show that this is two-site Bose-Hubbard model. Okay, so it is like Hubbard model with two sites, and there it is known that you have self-trapping. Okay, and there presumably, I'm not sure, there probably you can write more exact solutions in that limit, but this is only in this limit, but here it is true even without this limit. Okay, yeah. Okay, so but okay, okay. One more thing I wanted to say this is that, so we have a code in we have a MATLAB code that's uploaded, right? That I was telling you about. So actually in that code, actually if you just double that code, double the contents of that code and add this J term, okay, and remove, our code is written for driven dissipative JC model, so you can remove drive and dissipation, and just the Hamiltonian you sort of make two copies and add this term, and you can reproduce all these plots actually, okay, by adapting our code which is on the website. So I would encourage students to try that, and I can give some specific values of all these numbers so that they can really search for some interesting physics. Okay, so you can easily code this system, which Hari is going to explain how to code the Jaynes-Cummings model in today's tutorial. Not this setup, but just single Jaynes-Cummings model with drive and dissipation. Okay, so now let me come to the
Manas, I mean, so just one again. So I guess basically once you couple the two qubits, the conservation laws go away, right? I mean and that's why you can't solve exactly, right?
Yes, that is true. Yeah, so that conservation law goes away, and then you cannot solve. Yeah.
No, so then I was wondering, like, would one call this a non-integrable Hamiltonian? If you look at the spectrum, would it show like level repulsion? And do you know this is if?
Yeah, actually, I don't know whether people have calculated level repulsion for this actually. But what will happen is that if it is a non-integrable model and you actually calculate a level repulsion even for these kind of systems, you should see that the level repulsion will be like how it is for random matrices.
Okay.
Yeah. In fact, there is a model that I'm going to talk tomorrow about. That's a very, very important model, which is the decay model. Okay, and in the decay model, I will show that that's the level repulsion there actually matches for the closed decay model actually matches Hermitian random matrices and so on.
Oh,
yeah,
okay.
but that will be interesting to just calculate. literally calculate, diagonalize this problem and calculate the.
Yeah, because with your code, it gives the full spectrum, right?
That's right. That's right. Yeah.
Okay.
Yeah. In fact, yeah.
These total excitations are still conserved, like sum of qubits of both and like sum of photons of both. I mean, our code we had to sort of modify it to compute this level statistics to account for this conservation law. The total excitations are conserved, right?
I mean, yeah, total has to be conserved because otherwise where will it go, right?
Yeah.
So total has to be conserved. So A1 dagger A1 plus A2 dagger A2 plus sigma Z1 plus sigma Z2.
Yeah.
That will be conserved.
I think this looks interesting question. We can discuss, I think, more.
That's right. Right. But anyway, so that I think. So Abhishek, does that answer your question?
Yeah.
Okay.
Yeah, to think maybe it's a bit more, but it's
right. But I mean, I am so I know that we know that for decay model and things like that you have level repulsion which matches random matrix series. But for this, I mean, somehow people have not.
Still, there seems to be a extra conserved quantity, the total thing, but I don't know if that. It's difficult to say if one should call it an integrable or not. I mean,
right. So that's exactly. So it's not. It doesn't imply. I think it's not like in the decay model. What happens is that there is no conservation. The total number is not conserved. There the parity is conserved. So there you can have except if you are in even parity you can have 7, 9, 11 and so on. I don't know if that was important to get connections to random matrix theory, but this is something which we can just literally diagonalize and check.
Right. Yeah.
So
yeah. For small n, I think it looks like a small matrix. Maybe we cannot connect it to random matrix theory. I mean, so for large n, I think probably we can think of.
Right. Yeah. You take quite large.
Yeah. So I think the way one should do is like, let's say we choose n equal to n would be now basically n1 plus n2. Okay. And we should choose n equal to, like, say, if we choose some 64 or something, right? And it will just remain 64, right? And if this is large enough, I think we should be able to do that. Yeah. Right. Yeah. So I think so we can check this, but because in decay model also, Abhishek, same thing happens. You have to. It's not always true. There is some other parameter there, which is the spin, large spin and small spin. There is some other thing which actually decides the level spacing statistics. So presumably same thing happens here. If you do extremely small n's, I think you can't get. But yeah, I think we can do it actually. We'll actually try to do it. Yeah. Okay. Now let me just end with this very important thing of driven dissipative James-Cummings model, and it also sort of addresses Sanjib's question about various bath mechanisms and so on. So here is the story. So now we are back to single James-Cummings model. Okay, but so that was this piece. Okay, so that is this piece. So what you can do in experiments is basically you can drive the system. Okay, so till now I use the word drive quite a lot in the previous lectures, but I always used to say thermal drive. Okay, so that's a thermal drive, but here what they actually do is they do a coherent drive. Okay, this is like a single frequency drive. Okay, and here they drive the cavity. Okay, so you have this James-Cummings model. Okay, you have a two-level system in a cavity, and then you drive it with a single frequency, and you drive essentially the cavity. Okay, so these are all done. You can do it in experiments and so on. So now you see, now what are the various things? So now there's a driven quantum system, and truly driven, not just because of temperature or things like that. It's driven because of actual monochromatic drive, which they can tune both the strength and the frequency of the drive and so on. So now in addition to this, what are the other things? So the cavity is subject to a decay kappa. So we have independently studied cavities. Right, we independently studied harmonic oscillator, and there was a decay kappa. The qubit is subject to both the damping, okay, and dephasing. So dephasing we studied today, Okay, damping we did not study as such, but as I was answering Sanjib's question, you can mimic it by having this kind of terms as your HSR. Okay, if this is your HSR, you can use this HSR and systematically do the same business. Okay, derive quantum master equation, and you can mimic this damping. Okay, and with a little bit of approximation, you can reduce it to, it'll be Lindblad of sigma minus, Lindblad of sigma plus, and this kind of terms. And this is basically Lindblad of sigma z. Okay, so okay, so now what happens is that so to actually sort of explain a realistic situation, etc., you have to take into account all these things, and you end up getting a fairly rich driven dissipative quantum system. Okay, realized in experiments, and this turns out to be the Lindblad master equation for this system. Now let me explain this a little bit. Okay, so so first of all, this drive term is an explicit time dependent drive. Okay, so this drive term is basically in some rotating wave approximation, it effectively becomes like a time independent Hamiltonian. Okay, so the Hamiltonian that goes into this unitary part has the drive piece, but the time dependence is gone by something called a rotating wave approximation. Okay, and so this is the Hamiltonian and this is drive. Okay, so you see the drive term only has something proportional to A plus A dagger, and then you have all these different Lindbladian terms. So this is for cavity, this is for dissipation of the qubit, and this is for dephasing of the qubit. So of course, if you start from pure microscopics and do the procedure that I outlined in my previous lectures, you will not get this form because it will be more complicated. It will be in the Redfield form. But usually what one can argue and one can say is that in the parameter regimes of interest, especially in the experiments, you can really, add the Lindbladians separately as if they are just coming, independently. And usually that is for most of the experiments and most of the situations that is already, first of all, complicated enough. And at the same time, it captures all the necessary physics. Okay. And there are two kinds of Bose functions that enter. That is another important point. N bar of omega c, which enters with the cavity, and n bar of omega q, which enters with the qubit. Okay, so n bar of omega c is nothing but 1 over e to the beta omega c minus 1, and n bar of omega q is actually 1 over e to the power beta omega q minus 1. The beta is typically the same because these are all kind of placed in given some refrigerator and things like that. So the temperatures of the qubit and the cavity are basically the baths associated with the qubits and the cavities can be taken to be same. Okay, so that is.
So Manas, just quick question: this approximation, is it just expanding cos and just retaining the first term, or something else?
Which approximation?
This rotating wave approximation. It's more than just expanding cos and taking the first term.
It's more than that. It's more than that. So let me just go back to this cos. Okay. You see my screen, right? So So this is basically e to the e by 2 e to the I omega dt plus e to the minus I omega dt a plus a dagger. Okay. Now what we do is we introduce some rotating. We go to some frame where a itself becomes e to the minus I omega dta. Okay, and a dagger becomes e to the plus I omega dt a dagger. Okay, now what happens to this piece? This piece becomes e by 2. Now I'm going to multiply each other, so that will become a plus a dagger plus a e to the minus 2I omega dt plus a dagger e to the plus 2I omega dt. Okay. and you have to be a little careful with other pieces and things like that. Maybe I can add some details in the notes, but it's fairly simple to do. But then what you do is you basically remove these fast rotating terms, okay, and then you end up with this effective time independent Hamiltonian. Okay, so I mean, you don't and you don't necessarily need to do this. I mean, in fact, you can numerically speaking, you can yeah, maybe that's an important point. Numerically speaking, you can actually put the actual thing here, okay, and you might have to just do some RK4 and things like that to do the time dynamics.
And this one, what does it physically mean actually, this approximation?
Which the rotating wave?
Yeah. Because this A daggers are whatever the cavity, this thing, no?
Cavity frequency, cavity mode. Yeah. Right. So it's basically it basically means that you just
you keep changing the mode with time, or
yeah, I think it just means that you just go to the rotating frame of the drive. Okay? You go to the rotating frame of the drive, and then you do your entire calculation.
Okay.
Right, exactly. So basically, you go to the rotating frame of the drive, then everything is still slow there, right?
But then this changes the terms in like where this Z is there, no, or omega C is there. There, this A dagger A and A dagger A will not change, but this the coupling term probably this will change, right?
That's an important question. And what happens is that just like A dagger goes from A dagger e to the I omega dt, sigma minus goes in the opposite direction.
Oh, okay.
So that's the thing. I had no clue. I had no idea that I'll actually have time remaining. So I on purpose did not put the details here. But But yeah. So basically that's what happens. And essentially in that frame you do all the calculations. And if you are interested in some observable, that should be independent of which frame you are in, right? And then you are essentially done.
Okay.
So that is the idea. And in fact, what Hari is going to teach today is how to deal with this piece. He is literally going to solve this problem. So the tutorial that is there on the website actually has the PDF file, has some basic concepts and how to implement the algorithm. And along with it, there is a code which basically has this algorithm written already, and everything seems to be working. So one thing I want to say here is that very important thing is that the boson, the space here, of course, will be 2 times some n cutoff, right? 2n cutoff times 2n cutoff, and n cutoff you have to choose. Okay, let's say n cutoff is 20. But that's okay. You have to just be careful that your temperature and coherent drive are such that if you have too many bosons, then your n cutoff has to be larger. Okay, so that's the only thing that you have to be careful. But you have to just use a truncated space for the bosonic sector. Okay, so yeah, so I think I hope I did not go faster. I hope I did not go too fast, but actually I'm actually done with what I wanted to teach. And next class we will discuss the decay model and phase transitions and basically use all the machinery that has already been introduced by Gregory and also what Arnab showed about Bogolubov transformations. We are going to use those things to understand various features of the decay model in terms of phase transitions, chaos, things like level spacing statistics, and generally some bosonization techniques for decay model and some aspects of Z2 symmetry in the decay model. Okay, so I think I'm done here. If there is any other question about the driven dissipative model, I mean, just let me know if there's any question about this in combination with this. Okay, so that you know exactly what is going where. Maybe I should also mention that this here in this rotating frame, even the photon frequency gets shifted. Okay, so this is some subtlety, but you can easily do this. the photon frequency also gets shifted by the drive frequency, and the cavity frequency also gets shifted by the drive frequency. But the Hamiltonian is essentially a non-time dependent version with some shifted frequencies, and the light matter coupling, nothing happens to it. Okay, so I think I finished it mainly because I did not go to the details of the calculations of the exact solution. But I guess I'll leave it here because maybe it'll take time to. But if are there any questions or?
So that final Hamiltonian after rotate this thing. So if you take omega q equal to omega alpha, these terms disappear. So what does it mean in that frequency?
Omega?
No, if you take omega c equal to omega alpha, no, that one.
Omega d.
Yeah. So that does it mean anything or some kind of resonance or something? No.
Right. No. You can. I think you presumably will get some nice resonant features, but basically it means that your cavity frequency is somehow resonant with how you are driving it. Okay.
Yeah.
So this term disappears, but still you have A here. Okay. So it's not that A completely goes away. You still have A, and basically what happens is that you will get some enhanced features. So if you I mean there are many. Okay, so typically what happens is that if the drive frequency is the x-axis, okay, and which is what they do in experiments, they actually have a very nice way they can tune the drive frequency, and you calculate some quantity here. Typically what happens is that there is some resonance around the cavity frequency. Okay, so yeah, nothing. I don't think there is any divergence or something. It's just that you will see some nice resonant features around cavity frequency.
Okay.
Manas, can I ask a quick question?
Sure.
Yeah. So when you're doing this rotating, going to the rotating frame, so the system path couplings and all remains invariant. Is that guaranteed? Meaning the Limbladian that you write. So there, this extra phase factors in time, those factors doesn't contribute. Is that correct?
Yes, that is correct. Actually, what happens is that let us pick one.
Because there is a quadratic, like A dragger kind of term.
Exactly.
Okay.
So I have worked it out very carefully. Actually, even if I do this has some pieces like this, right? Sigma plus rho, sigma minus.
I got it now. And the other question is that these thermal factors that you are writing, n bar or n bar omega c or omega q, so they are omega c or the shifted frequencies?
This one?
So this is it omega c or omega c minus omega d? So like because you're going to the rotating frame where the frequencies are getting renormalized. So
right. So no, I think okay. Let me try to work it a bit more carefully, but I think we should be able to work it out. So we don't have to worry about this whole piece. Just take a empty cavity and drive it. Okay.
Right.
Empty dissipative cavity and drive it. And okay, the question is this just needs a little bit of working. But question is whether you calculate this or this also you calculate at this shifted frequency, right? That's the question.
Right.
Manas, this is like the phenomenological master equation, right? We sort of add drive like after sort of doing this local thing. Yeah, it's like by hand we sort of add.
That's right.
So in that sense, it appears at omega c and omega q only, right? I mean,
I think
those are just coefficients, right? We don't derive like master equation consistently, like keeping the drive and all that.
True, but the question is, I guess that's why I said if you forget that Jaynes-Cummings model, and let's say that you go to this problem, empty cavity, okay, with the drive, okay, and then do that not phenomenologically, actually do that carefully.
There you would find that it's omega c minus omega.
There my guess is you'll find that, but I think but given the fact that we have a much more complicated system with Jaynes-Cummings unit, probably I guess we probably just leave this whole piece phenomenologically itself.
Okay.
Right. So yeah.
Thank you. Thanks, Manas.
Yeah.
Sir, I had a question about the Hamiltonian that you wrote about the driving.
Yeah.
Can you just go a bit up?
Yeah.
So yeah, so in the driving term is basically like a dipole kind of this thing, right? Electric field, and it will so like E dot D kind of term, right? The interaction. So like, shouldn't there be the system operator like sigma plus sigma minus shouldn't be there in the last drive, right?
No, no. Okay, so that's a very important question. So remember, so the way many of these experiments are set up is just the cavity is driven. Okay, the cavity is driven, and this
Okay.
cavity just happens to host a qubit. Okay, so that is just an experimental setup. But indeed, you're right. If you want to actually drive even the qubit, then you should add a term like this: E cosine omega dt, presumably sigma x or something.
Okay.
Okay, so the experiment is set up in a way that there is some input that goes into this cavities, and only the cavity is driven. Okay, so you can
Okay.
think of the fact that I'm just coming and placing a qubit inside a cavity which is already driven. Okay, so yeah.
Manas?
Yes.
Yeah, so I have a question that let's say instead of using a spin half system, let's say I replace it by a spin one system.
Yes.
And so whether it's a driven system or a non-driven system, so should I expect that the features that we are seeing will be followed there in the spin one cases also?
You mean in the either driven or non-driven cases, right?
Yes. So
yes. I think so. I mean, yeah. I mean, it should work with basically it should work with higher spin systems also.
okay.
So let me just try, maybe answer it a little more concretely. So one thing which I'm going to do even in next class is that, okay, so this is cavity, okay, schematic of my cavity. So whenever I write this, I just mean A dagger A, okay, with maybe some kappa. Now imagine you put one two-level system, okay. Now what if I just add one more two-level system inside the cavity?
Right.
Okay, so this is okay, this is two-level systems, but what I'm going to answer in the next class is what if you have n of these two-level systems, okay, and then something very interesting happens with these n two-level systems, and that's what I'm going to discuss. But just to answer your question, I think it should not. I think it should go through. I mean, at least you should be able to do all these calculations. Yeah.
Okay.
I don't see anything that prevents you from doing it for some other spin system. Yeah.
Thanks.
Yeah. Okay, so there is a question here on the chat window. The question is, I missed how you could find the critical value of JC. JC will be order of square root 10 for JC due to bad connection. Can you read it? No. So okay, so no. This is a very tricky thing. Okay, so this is where it goes back to even Abhishek's point that you basically do direct numerics of this. Okay, you pick some G, and you keep doing direct numerics, and you suddenly see that there is a GC which after which it suddenly changes. Okay, it becomes self-trapped. Okay, now you basically have some value of GC. Okay, now you have some value of GC for N1 equal to 20. Okay, now you make N1 equal to 10 or N1 equal to 30. Okay, and again calculate GC. And it just turns out that GC goes as square root of N. Okay, so at this moment, I don't think there is a rigorous understanding why it is like this, but this is just it's an observation. So in other words, okay, so physically, what does it mean? Okay, so the physical meaning of this is interesting. So I hope I'm correct about the square root part. I think there is square root 10. Yeah, there is square root 10. So imagine n is equal to 20. So then GC is like square root of 20. Now imagine n is equal to 50. So what is n, right? N is the number of bosons in the first cavity, and number of bosons in the second cavity was 0, and qubits you can ignore. Qubits, let's say both qubits were down or something. Okay, by ignore I mean you have to have the light matter coupling, but qubit, let's say it's in some state, maybe both the qubits are down. Now if n is root 50, n is 50, GC is root 50. So what does it mean? It means that if I increase n, my critical GC increases, right? Which means that if I increase n for the same value of G, I may miss self-trapping, right? So imagine my G is some value, but I keep on increasing n, my GC will move to the right. And that means that if I increase n beyond a point, I will lose self-trapping, okay? And I will, and basically it will just completely overflow to the other unit and so on and so forth. So the critical point, the critical GC gets shifted a bit, that shift goes as root n. Is that clear? Okay. 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 So I think
there are no other questions. Okay, so maybe we stop for today. Thanks, Manas. See you tomorrow.
Thanks.